This video will explore the computer as the bicycle for the mind, a tool designed to amplify our intelligence. Just as the bicycle amplifies a human's locomotive efficiency, the computer amplifies our ability to process information. To understand this tool, we will deconstruct it from the sand up. At its core, computing logic is the strict mapping of inputs to outcomes. The fundamental premise is simple. If this happens, then that happens. Then we get a result. Computer circuits like the AND and OR gates map inputs to defined outputs, which we see illustrated in their truth tables. The history of computing is a quest for speed without moving parts. Early computing used slow, massive relays. Vacuum tubes were faster, but hot and unreliable. The transistor solved both problems, providing a switch controlled entirely by electricity, with nanosecond switching speed. The transistor works by doping pure silicon, an insulator, with impurities like phosphorus N-type or boron P-type. This creates free electrons and holes. Applying a small voltage to the base allows a larger current to flow across the depletion barrier, acting as an electrical valve. Transistors are combined to form logic gates that physically embody truth tables. Two transistors in series create an AND gate, while two in parallel create an OR gate. The XOR gate, essential for addition, outputs one only if inputs are different, building blocks of complexity. Computers use binary or base 2 because it matches hardware reality. High voltage is 1, low voltage is 0. With just 4 transistors, we can represent 16 unique values. Scaling up to 8 bits allows us to represent 256 values. To add numbers, a computer uses an XOR gate for the sum and an AND gate for the carry to the next column. This simple logic, called a half-adder circuit, is the foundation. To build a 4-bit adder, we need 64 transistors, illustrating that complexity is just layered simple addition. Memory involves trapping and looping. Long-term storage, like flash, traps electrons in a floating gate to block current, even without power. Short-term memory, or latches, uses feedback loops where a gate remembers its previous state, requiring constant power. The microprocessor integrates all components, adders, memory, and control logic, onto a single chip. The clock signal, oscillating at billions of cycles per second, acts as the orchestra conductor, triggering the next operation every tick. Modern processors perform hundreds of billions of operations per second. The translation stack moves from high-level code, like C, down to voltage. A compiler translates human logic into assembly instructions, which are then translated into machine code, a stream of ones and zeros. This stack lets us command billions of switches without touching binary. When sensing reality, computers prefer binary inputs, like a simple float switch that is either open or closed. However, analog inputs, like a thermistor that changes resistance based on heat, require translation because the computer only understands ones and zeros, not continuous curves. To digitize the analog world, we use an analog-to-digital converter, or ADC. The ADC uses a ladder of comparators to measure input voltage against known reference points. This process slices the voltage range into distinct steps, allowing for linear approximation between those points. Custom hardware, like the ECP103 microcontroller, is built for efficiency and safety. This chip manages hood ventilation by running fans at variable speeds based on local temperatures. With only 64 kilobytes of memory, the code must be clean, efficient, and reliable. The nervous system, represented by Modbus and SCADA, enables control over long distances. Modbus is a communication protocol, and SCADA provides the gateway that translates local signals for the internet, allowing a user to remotely monitor and control equipment. We have demystified the stack from transistor to global network. Now we use massive global datasets to describe how equipment performs. The next step is machine learning, using this data to predict faults and optimize comfort automatically. We have built the bicycle. Now we are learning to ride it faster.